So thank you very much for the organizers and the people who attend the conference to be here. I am very happy to speak about this subject. In fact, for me, it's the second time. 2 years ago, I gave exactly the same series of lectures, or almost exactly. But I like this, so I am happy. I will speak about actions of groups on the real line, so the most simple manifold, and by homomorphisms. And so the goal is to of the lecture, I think I will be more precise today, is to prove a statement that lattices of higher rank in semi-simple Lie groups of higher rank do not act on by homomorphism on the real line apart by trivial actions. And so this statement is part of the Zimmer program. So of course it is very related to the subject of the workshop. And so this statement, I will be more precise today. I think I will give examples of actions of lattices and explain why there are some difficulties for them to act in higher rank in examples. But so in this series of lectures this week, I will speak more about ingredients and tools that will be useful for the proof of that statement. And really the proof of that statement, I will prove then that in the workshop at IHP in 2 weeks, Paris. So let me just begin with a very simple fact, which is, I think, extremely beautiful. So, of course, maybe the Zimmer program belongs to a general question, which is very crazy question, is if you start with a manifold, you might try to understand what kind of groups act on that manifold. And this is a very vague question. But it turns out that in the case of the manifold, the simplest manifold, the real line, there is a very simple answer to that question. And the answer is the following proposition. I will begin with this. So it completely answers the question if you take a countable group, for countable groups. So if you take such a group gamma and you ask whether it embeds in the group of homomorphisms of the real line, I will put a plus here. So this is not really a big deal because it's an index 2 subgroup. If and only if it is left orderable. So I will use this abbreviation in the lectures. So which means that so there exists a total order on gamma, which is invariant by left translations on gamma. Namely, if you pick a triple of elements in gamma, so then G is less than H if and only if when you multiply by K G and H, you keep the same order. Okay? So it makes the question of action on the real line by homeomorphism, preserving the orientation. The plus means that you have a homeomorphism that preserves the ordering on R. There is a question? Oh, sorry. So it makes this problem into a completely algebraic one. And let me just, I will not give the complete proof of that. Maybe it could be, so to complete the proof that I will give should be a very nice exercise. But let me just give some words about the proof. So first of all, suppose that gamma is a subgroup of Omeo. So how can you find a left order on the group? So it's the following thing. If you take a dense Xn is a dense sequence of real numbers. So then I will define, so G is less than H. So Gn, I take two elements in gamma. G is less than H if and only if. Let me just write. So G is different from H, and so if I look at the infimum of the indices such that G of Xn is different from from H of Xn, so then sorry. So to understand this definition is that, so of course, if you have G is different from H because the sequence is dense, there is some n such that G of Xn is different from H of Xn. And so you take the inf of all these indices and you look at the orderings of these two real numbers, G of f of Xn0 and H of Xn0. And that gives you the ordering of the group. It's really easy to show that this ordering is left invariant. Namely, if you multiply on the left by an element k, you will keep exactly the same ordering. So this ordering is called. So in fact, there is a very nice and important paper by Andrés Navas in around 2005 or 6 or something like that, where he introduces in the theory of left orderable groups techniques of dynamics in one dimension based on this proposition. And in this paper, he called this so the relation between the order and the, maybe I should say this a little bit later. Sorry, I will go to the, so here we proved one of the implication of the proposition, and what I wanted to say about Navas' work is for the other implication. Sorry, so let me just go to the other implication. So now suppose now that gamma is a countable group having a total order invariant by left translations. So this total order I denoted again by the same symbol. And then we want to find an action of the group by homeomorphism of the real line. And what we do, we will pick a numbering of the elements and we will use this ordering to define an embedding of the group gamma into the real line to R, which preserves the orientation, so which preserves the order. And we will try to prove that the action on the group on itself, which will give an action on the image of this embedding by transformations that preserve the order, and we will try to extend this action to the closure of this embedding, and then to the whole real line. So the thing is that if you start with any, so the key is to define an embedding gamma into the real number. So this is a and so the action of gamma on itself by left translation, which preserves the order, will act on the image of this embedding, just by conjugacy. And this action on the image will preserve the order, and then we have to argue that we can extend this action by an action by homeomorphism. The point is that not every embedding will work. We have to define certain kind of embeddings so that this strategy will work. And so there is one embedding which works. This is not at all the only one, but just so it depends on the numberings that we chose at the beginning. So let me just explain how we do. So we will define inductively the image of the element Gn by T. So T of G naught is chosen to be 0. And now assume that T of G naught, T of G1, etc., T of Gn have been defined. And then we want to define T of Gn plus 1. So there are three cases. So the first case, there is a blackboard there. Okay. So the first case is that if Gn plus 1 is larger than all of G naught to Gn, So then we will put T of Gn plus 1 on the left of all of these guys. So namely, so we will define T of Gn plus 1 by this formula. So in the case where we will do the same thing if Gn plus 1 is less than all of the GKs. So namely, but in that case, we will put T of Gn plus 1 on the left, on the left side. So if and now if Gn plus 1 is in between two of them, so say yeah, GA so if we have GA less than Gn plus 1 GB and either for any k between 0 and n, either gk is less than ga or gk is larger than gb. So it's better to say that with words. So if Gn plus 1 is in between two of the G0 to Gn, I call them Ga and Gb. So then we define T of Gn plus 1 as being the middle point. Okay? And so this is a way to define an embedding of gamma into the real numbers, and this embedding clearly preserves, so it is order preserving. And so the point, which I think is a good exercise to do. So now we can look at the action. So gamma acts on T of gamma by, so G of T of Gn. By definition, this is T of Ggn. Okay? And of course, on T of gamma, we have the order given by the real numbers. But because T preserves the order, this action of gamma on T of gamma preserves is order preserving. And in fact, what we can prove is that with this specific choice of T, that the gamma action extends to a continuous on the closure of T of gamma. Okay, so this is an exercise. This is not completely trivial to do. It's elementary, but there is a reasoning to do, and it has. So here we really have to use this specific choice of T. In fact, there is a larger class of T which will work for that, but. So we get a continuous action of gamma on a closed subset of the real numbers, which preserves the ordering. And now we extend this action of gamma we just need to on the components of its complementary regions by affine maps. So we have a certain subset closed. This is T of gamma. We take the components of the complementary of of this closed subset. Here is one of them. So we will extend the action by saying that an element gamma is going to send such a component to another one by an affine map, an affine transformation of the given intervals. Okay, so there is a little reasoning to do. So namely, we have to prove that the extremities of these components are mapped to extremities of certain components, and to extend the map by the given affine map. And I skip this. This is part of the exercise. Okay, so this ends the proof of this implication of the proposition, namely that if we have a total order on a group which is invariant by left translation, in fact we get an action of the group by homeomorphism of the real line, preserving the orientation. And now I can say what I was saying at the beginning. So namely, I was saying about this work by Navas. So the work by Navas was, so he introduced dynamical methods in the theory, which the algebraic theory of left orderable groups, using this procedure. So namely, if you have an order, you can look at an action of the group on the real numbers, and you can try to import methods of dynamics to study the orders. It is a very powerful method. The article of Navas is very interesting, I think, and profound. And this way of assigning an action of the group on the real numbers given an order is, so the action is called in the terminology of Navas, it is called the dynamical realization of the order. And in fact, you can prove a certain number of things. So first of all, you can prove that up to conjugacy, this dynamical realization does not depend on the given numbering of the elements of the group gamma. It's not completely trivial to prove. You have plenty of ways of numbering the groups, and it will give you different kind of actions, but they are all conjugates up to homeomorphisms. So essentially, this dynamical realization is completely well defined when you have at hand a given order invariant by left translations.
Just to be sure,
yeah.
This is not the one that we constructed, or this is the it proved that this one are
so
or that it's another one, another kind of relation.
No. This one, so the one that if you start with an order, we given a numbering of the elements of gamma, we defined an action, and this action is well defined. So if you change the ordering of the numbering of the elements of gamma, the other you define another action, but they are conjugate up to homeomorphism. So, and we call these actions the dynamical realization of the order. Okay. Okay. Okay, I wanted to say that we will focus on the notion of left orderability of groups in the lectures, but there are other kind of notions of orderability of groups. I will, in fact, not speak about them, but just I wanted to say that there is a whole theory. So, for instance, there is a notion of B-orderability, so an order which is invariant on the left and on the right. This is completely another story, and there are also plenty of other notions, but we will focus really on the left orderability because of its relation with the Zimmer program, with the actions of groups on the real lines. Also, I wanted to say that in the Zimmer program, there are a number of questions which concerns not actions by homeomorphism, but by diffeomorphisms. And these really nice proposition and simple proposition do not work at all if we speak about actions by diffeomorphisms. Namely, there are some groups that are left orderable, countable, even finitely presented that are left orderable but do not have any actions by C1 diffeomorphism on the real lines. So if we speak about differentiability, the story is completely different, and I will not speak about this in the lectures. It is really another story. And what is the question that I would like to discuss in the lectures is to discuss the left orderability of lattices in semi-simple Lie groups. So the question which belongs to here really to the Zimmer program is which lattices gamma in a semi-simple Lie group are left orderable, or which is equivalent, have a non-trivial and faithful action on the real line by preserving orientation homeomorphisms. And I would like to spend the remaining time of this first lecture to give some examples and to right. So first of all, I think this has been defined, but so semi-simple Lie groups are so at least if they are center free, they can be thought of the isometric groups of symmetric manifolds, symmetric spaces. And let me just recall what is a rank. I think probably this has been defined in the previous lectures, but so if G is the isometric group of a symmetric space, which I will have in mind in at least in this lecture. So then the rank of G over the real numbers is the maximal dimension of totally geodesic flat. So a flat is a submanifold which is isometric to an Euclidean space, or copy of immersion of the Euclidean space. And so let me just, so the thing is that let me just give some examples of left orderable groups, lattices, and to begin with, I will speak about the case of the simplest one. In a sense, which is a hyperbolic plane. Okay, so the thing here is that we can prove the following fact, or say lemma or proposition, I don't know. So any torsion-free lattice of so I would put a plus here just to have a connected group, is left orderable. Okay, let us prove that. So there is here I said torsion free. So of course, to have torsion, so if there exists a non-trivial element whose power is the identity, it's a neutral element of the group, this is an obstruction to have a left order, because if you have a left order, an order invariant by left translation, so if gamma is different from the identity, from the neutral element of the group, so then, for instance, gamma is going to be bigger than the identity, and then gamma square is bigger than gamma, etc. And so you never go back to the identity. Okay? So if you have a left orderable group, any non-trivial element is of infinite order. Okay? So of course, at least for the question of that we are discussing, if you start with a lattice, if you want it to have a left order, you have to assume that it is torsion-free, so namely that every element has infinite order. But in the case of the isometric group of the hyperbolic plane, this is a sufficient condition. In fact, this is probably the only Lie group, semi-simple Lie group, with this property, that any torsion-free lattice is left orderable. So let us do the proof of that, or indicate some elements for the proof. So in fact, what we have is that if you have an action of any subgroup of the isometric group of the hyperbolic plane, it acts on the boundary at infinity of the hyperbolic plane. You know that this boundary is a circle, and so you get an action. So by, in fact, diffeomorphism acts on the boundary of the hyperbolic plane. This is a geometric boundary. There are many models for the hyperbolic planes. For instance, I don't know what is your favorite one, but one of the model is a unit disk, and the action is by Möbius transformation. And so this boundary is just identified with the boundary of the disk in this model. But there are plenty of ways of defining this. I will not do so in the lectures. And here, this is a circle. This is a one-dimensional manifold, compact, diffeomorphic to the circle, that I will think of as being the realigned mode Z, okay, the quotient by the integer translations. And so what you can try to do is try to lift the action of the lattice to an action on the real line, okay? So the question that you might ask is it, so given gamma inside is it possible to lift the action of gamma on the boundary to an action on the universal cover of the boundary, which by this identification is identified with the real numbers, okay? And if you are able to do so, because the action of gamma on the boundary preserve the orientation on the boundary, you will get an action by orientation preserving homeomorphism on the real line, and you are happy. You know that the lattice is left ordered. So yeah, we just go to the sides. In fact, the answer to that question is negative in general. There is an obstruction, a topological obstruction for lifting the action, which is called the Euler class. So this is a cohomology class in the second cohomology group of the group gamma. But I would like to say, before explaining what is this obstruction more in details, that if gamma is a free group, so let us just analyze the first case, is that when gamma is freely generated on a finite subset S inside gamma of generators. So then it is, so the answer to that question is positive. So then we can lift individually each element of the generator set to a map S tilde from the universal cover of the boundary to itself. And because we have no relations between the generators, this defines a lift of the action of gamma. Because by assumption, we have no relations. Those S tilde define a lift of the action of gamma on the boundary to an action of gamma on its universal cover. So in this case, there is no obstruction, and in fact, the second cohomology group of the free group is trivial, so that explains why in that case, we can do that. So, of course, this case corresponds to, in the case of the hyperbolic plane, this case corresponds to the case where the associated locally symmetric space, so namely the hyperbolic plane divided by the group gamma, is a non-compact surface. It will be a non-compact surface. Let me just, with at least one cusp, it will be a surface of finite volume with at least one cusp. And we know that in the theory of surfaces, that the fundamental group of non-compact surfaces are free. And so this case corresponds to the non-uniform case. In the case, let me go to the. In the uniform case, however, there is an obstruction. And let me just give some words about that. So gamma is the fundamental group of a closed hyperbolic surface. And we know by classification theory of surfaces that in that case, so the fundamental group has a presentation so, etc. So we have 2G generators, where G is the genus of the surface, and the only relation is that the product of the commutators is equal to the identity. Okay? So in the picture here, in the case where the genus, the number of holes is equal to 2, so the AIs and BIs can be chosen in this way. As usual. And so in that case, what we can do is the following. So let me just define the obstruction, so the LR class in that case. So we can do the same game, try to do exactly the same games as we did before. So we can lift. So the system of generator S, as before, is now the AIs and BIs. So we can lift the AIs and BIs to homeomorphisms AI tilde, BI tildes of the universal cover of the boundary of hyperbolic plane. And those lifts will define an action of gamma, a lift of the action of gamma on on the universal cover of the boundary of the hyperbolic plane, if and only if we have that relation which is satisfied. Okay, so we can look at these relations. And now this relation, so this is a homeomorphism of the universal cover of the boundary of the hyperbolic plane, which descends to the identity on the base. So it is a covering map of the covering. And this covering map is given by just an integer, because the fundamental group is of this circle is just the integers. So this is an integer, and in fact you can verify, this is very easy, that this integer does not depend on the choices of the lifts AIs and BIs that you have chosen. So this is a deck transformation of the covering which identifies with an integer. Okay, because this the fundamental group of the circle again is equal to the integers. And this integers is exactly the obstruction in that case. This is the Euler class, and you can do the exercise for those. It's not a completely trivial exercise, but let me just say that. So in this case, if you do that with this presentation, this integer is not 0. It is equal to the Euler characteristic of the surface. It is equal to 2 minus 2g. So this is the bad news. Is equal to up to sign to the, it depends on the orientation that you have chosen for the presentation, but and the Euler characteristic of the hyperbolic surface is not 0, so you cannot lift this action. However, we can do a thing, and here I would like you to believe a little bit what I will say, is that we can. So if you start with so the identity representation of gamma inside the isometry group of the hyperbolic plane, so you have this Euler class which is not 0, but you have plenty of other representation of other morphisms from gamma to the isometry group of the hyperbolic plane, for which this Euler class is going to vanish. So to circumvent this bad news, we will do the following. So we will modify so maybe better to say we'll choose another representation of gamma in this Lie group, the isometry group of the hyperbolic plane. And in fact, so let me just tell a little bit the story, but then this is here that I would like you to believe me, because I will not have time to enter into those details, is that if you look at this, at the set of all these representations of the group gamma inside the isometric group of the hyperbolic plane, there are several components. Each of those components are given by this integer, so the Euler class. And you can look at the component, which is the one that contains the trivial representation, so the representation mapping all the AIs, BIs to the identity. And the component of the set of all representations that contains this trivial representation, in this component, the Euler class, this integer, is constant equal to 0, because for the identity representation, of course, we can lift the representation to represent the action, to an action on the universal cover of the boundary. And you have to believe that in that component, you have some faithful representation of gamma inside this group. And in fact, this is not completely, so this is not very difficult to argue that, so in So we look at the component of the set of all morphisms from gamma to that contains the trivial representation. So what is good when you do that, when you choose such a representation, as I said, is that there is no obstruction. You can lift the action that you get from this representation of gamma on the boundary of H2 to an action of gamma on the universal cover. And so if you know that in that component you can find such an action which is faithful, then you win. You will lift the action, and of course, when you lift, the faithful property remains. Okay, so discrete, you don't need discrete for the reasoning that I'm. In fact, they will not be discrete. Okay, you just if you have a morphism from gamma to this group, even if the image is not discrete, you still have an action on the boundary through a non-discrete group. And if you have not this obstruction for the image of the generators by your representation, you can lift by exactly the same reasoning the action to the universal cover of the boundary, and if the action were faithful, you will get a faithful action of the group on the boundary, on the real line. Sorry. Okay. Yeah, so the action of your group on the real line that you will get will not have discrete properties, nor on the circle, but you just need an action, a faithful action on the line by homomorphism. So it will be dynamically very interesting, actually, this action, but and really rich. It will not be discrete. It will. But this is a way to see that surface groups are left orderable. There are plenty of other ways, and in fact, much more is true that lattices in the isometric group of H2, so surface group and free groups, are bi-orderable actually, and you won't see this bi-orderability with this method. But just I wanted to present some methods to get actions of surface group. It's not completely clear to prove that surface group are left orderable, nor free groups actually. It's not completely trivial thing. Okay, so let me go. I don't know. I have to. Okay. Yeah. Okay. Actually, I don't wanted to. So let me just tell you a little bit about So in fact, in the case of lattices in isometry group of hyperbolic space, if you go to hyperbolic space, the situation is very interesting. And in that case, there is a completely fascinating conjecture. I will not speak about that, but that says that. So in that case, if you go to 3 dimensions in the hyperbolic context, this is no more true. This proposition, namely, you have torsion-free lattices of the isometry group of hyperbolic space that are not left orderable. For instance, the Weeks manifold groups were proved by Caligari and Dunfield that not to be left orderable, but there are many other groups that. And there is a fascinating conjecture saying exactly which lattices are left orderable. This is related to foliation theory and to Fleur homology, and this is another stuff. But there is something which remains true and which probably is true for any hyperbolic spaces, is that maybe, so let me just say that in the context of, so maybe questions. So is it true that a lattice in isometry group of hyperbolic, real or complex hyperbolic space is virtually left orderable? I think this is a very nice question, and so the answer to that question in the case of H3 is completely is true. This is due to work of Agol and to work of Olsen, Vist, and sorry, I forget a name. But anyway, I can give you that name later. And we have examples in higher dimension of left orderable lattices, but there is no evidence if this question should be true or not. In the complex case, we have also examples in complex dimension 2, but we have no more examples in higher dimension. And maybe I will finish with this. So in the case of rank 1 symmetric spaces, so we have the quaternonic hyperbolic spaces and the Cayley case. Those, so in this case, so I would say that probably the lattices are not left orderable, and this is related to a question. So those groups have property T. This is related to the following question, which is probably very hard. Does there exist? We don't know any example of that. A left orderable group with property T. So I would suspect that, so I don't know for this question, but for the Cayley case and the hyperbolic quaternonic space case, the isometry groups have property T, and I would suspect that left orderability is not true, but I think those are very interesting questions. So I will finish that here, and thank you for attention.